Okay, let's dive into this. Every single time you save a photo, or fire off a message, or even just type one letter, your device has to remember it. But have you ever really stopped to think about how? I mean, how does a chunk of metal and silicon actually hold on to information?
It's a huge question, right? Our brains, they have this incredible squishy web of neurons for storing memories. But a computer, it's got none of that. It's all just electricity and a bunch of super simple switches. So how on earth does it go from a basic on or off state to storing, well, pretty much the entire internet? The secret, it turns out, is a really clever trick of logic.
To get our heads around memory, we first have to look at logic that can't remember. This is called combinational logic. And the best analogy is a doorbell. You press the button, it rings. You let go, it stops. The output, the ringing, only depends on what you're doing right this second. But logic with memory, sequential logic, that's a whole different beast. It's like a light switch. You flip it on and it stays on, even after you take your hand away. It remembers what you did. That's the whole ball game.
So here's our game plan for this explainer. We're going to trace that exact idea. We'll start with the problem of memoryless logic, then we'll uncover the secret sauce of sequential circuits. We'll meet the very first basic memory unit, it's called a latch, see how it got a major upgrade to become the much more useful flip-flop, and finally, we'll meet the whole family of flip-flops that are pretty much the foundation of our digital world.
So, how do you actually make a circuit remember something? The big idea is honestly so simple it's brilliant. You make the circuit talk to itself. You create a loop where the output can circle back around and influence the next input.
Check this out. In a normal logic circuit, information just flows one way, right? Inputs come in, they go through some logic gates, and an output comes out. End of story. But look at a sequential circuit. You see this memory element? Its output loops back around to become one of the inputs. The circuit can now see its own past. And that feedback loop, that is the absolute foundation of memory.
So the formal definition is, well, it's pretty much exactly what we just saw. A sequential circuit's output isn't just about what's happening now, it's also about what happened before. This is what lets it store binary information, a single 1 or a single 0.
Okay, theory's cool, but let's actually build one. The most fundamental, the most basic building block of all digital memory is a little device called a latch.
The fancy term here is bistable, but all that really means is that the circuit is perfectly happy sitting in one of two states, representing a 0 or a 1, and it will just stay in that state until you tell it to change. It's our light switch, and it's built to hold just one single bit of data.
And here it is. This is what one looks like, built from a couple of really basic logic gates. This is called an SR latch. S stands for set, which you can just think of as store a 1, and R stands for reset or, store a 0. You just send a quick pulse to one of these inputs and you can flip the latch into the state you want it to remember. Now, let's walk through this behavior chart because this is where the action is. If S and R are both 0, the output Q doesn't change. See? It's remembering. If you make R 1, it resets the output to 0. Make S a 1, it sets the output to 1. Simple enough. But, look at that last row. What happens if you try to set and reset at the exact same time? The circuit basically freaks out. It enters an invalid, unpredictable state. And that's a major, major flaw.
This was the exact problem that early computer engineers were banging their heads against. The latch was an amazing first step, but it was unreliable. It was a little bit wild. If you're going to build complex machines, you need perfect timing and total control. They needed an upgrade.
And the solution they came up with was honestly just brilliant. They introduced a pacemaker for the circuit, a timing signal called a clock. From now on, the circuit wasn't allowed to react whenever it felt like it. It could only change its state at very specific controlled moments in time, all dictated by this clock pulse.
Okay, so this is probably the most important difference to get. A latch is level sensitive. That means it's listening for changes the entire time the clock signal is on. That long window of time can lead to all sorts of weird, unpredictable behavior. A flip-flop, on the other hand, is edge-triggered. It's so much more precise. It only pays attention for a literal instant, the exact moment the clock signal goes from low to high or high to low. It's surgical precision.
And this waveform shows it perfectly. See the flat top part of the pulse? That's the level. A latch is listening that whole time. But the flip-flop, it only cares about the edge, that super sharp vertical line where the signal shoots up or drops down. Everything across the entire chip happens in that one synchronized moment.
So once this idea of the clocked edge-triggered flip-flop was nailed down, engineers just went to town with it. They developed a bunch of specialized versions, creating a whole toolkit of memory components, each with its own little personality.
First up, the SR flip-flop. You can basically think of this as our old latch, but now it has a bouncer at the door, that clock input. It only listens to S and R when the clock says it's okay. It was a massive improvement in stability, but if you look closely at that table, yep, it still has that dreaded invalid state if S and R are both high. It kind of inherited the family flaw.
So how do you fix that invalid state for good? Well, you invent the D flip-flop, which is pretty much the workhorse of the entire digital world. The D stands for data, and its design makes that invalid state physically impossible. Whatever value, a 1 or a 0, is at the D input when the clock edge hits, that's what gets stored. That's it. It is a pure, simple, and unbelievably reliable 1-bit storage locker.
Okay, so if the D flip-flop is the reliable workhorse, the JK is the clever problem solver. It looked at the SR's invalid state and said, hey, I can make that useful. When both the J and K inputs are 1, the flip-flop doesn't crash. It toggles. It just flips its output to the exact opposite of whatever it was before. This one little trick makes it incredibly powerful for stuff like building counters.
And you know what? That toggle function was so useful, it got its own specialized stripped-down version, the T flip-flop. Its entire purpose in life is to toggle. If the T input is a 1, the output flips on the next clock pulse. If T is 0, it just stays put. It's a perfect example of engineers creating a very specific tool for a very common job.
So let's just zoom out and recap our journey real quick. We started with a big problem. Simple logic circuits can't remember a thing. The elegant solution? A feedback loop, creating what we call a sequential circuit. Our first try was the latch. It worked, but it had a critical flaw. The big refinement came with the flip-flop, which added a clock for precision timing. And that single innovation sparked an entire family of devices, each one tailored for different digital jobs.
So why does mastering this one tiny little circuit even matter? Well, here's why. Because every single bit of RAM in your computer, in your phone, is built from a tiny circuit that acts just like one of these flip-flops. We're not talking about 1 or a million. Modern memory chips have hundreds of billions of these fundamental memory cells, all ticking away in perfect time with a central clock.
And that kind of leaves us with a fascinating thought, doesn't it? If these simple, elegant circuits are the atoms of memory, the basic Lego bricks, what happens when you start combining them in even more complex ways? What other digital structures, maybe even the very core of a processor itself, can you build from these fundamental blocks of just remembering a 1 or a 0?